These are the world's most audacious energy experiments, bold bets on technologies that could power the next century. From fusion reactors trying to capture the power of stars, to advanced nuclear plants rising in desert sands, brilliant minds are pushing the boundaries of what's possible in energy. Some will revolutionize how we power civilization. Others will teach us what doesn't work yet. But all represent humanity's boldest attempt to engineer the energy of the future. This is the story of 8 megaprojects building the energy of tomorrow. And it starts with Microsoft's co-founder betting $2 billion on nuclear technology that's never been tried before. America's nuclear comeback isn't happening in a lab or on blueprints. It's happening in the Wyoming desert, where Microsoft co-founder Bill Gates is betting $2 billion on the most advanced reactor design in decades. This is TerraPower Natrium, and it's not just another nuclear plant. It's a completely different approach to atomic energy that could change everything. While others build conventional reactors with pressurized water, TerraPower uses liquid sodium as coolant. While others struggle with energy storage, Natrium comes with a built-in molten salt battery that can store energy for hours and boost output by 50% when the grid needs it most. The reactor produces 345 megawatts normally, but can surge to 500 megawatts using its integrated storage system, like having a nuclear plant and battery system in one package. Construction began in June 2024 on the site of a retiring coal plant in Kemmerer, Wyoming, a perfect symbol of America's energy transition. The same community that once powered the nation with coal will soon power it with advanced nuclear technology. TerraPower isn't just building a reactor, they're proving a concept. Sodium coolant operates at normal atmospheric pressure, eliminating the risk of explosive steam releases. The liquid metal transfers heat more efficiently than water, and if power is lost, the system shuts down automatically without external intervention. Bill Gates has been working on this design for over 15 years, pouring hundreds of millions into research and development. The Department of Energy committed up to $2 billion in federal support. Private investors added another $830 million. But the real innovation is the business model. Instead of building each reactor from scratch, TerraPower plans to manufacture standardized components in factories, then assemble them on site. It's nuclear power meets mass production. If it works, Natrium won't just power 400,000 homes in Wyoming. It could become the template for replacing America's aging coal fleet with advanced nuclear technology. While America bets big on sodium and molten salt in Wyoming, something even more extraordinary was already rising from desert sand 7,000 miles away. The United Arab Emirates, UAE, built not one but 4 nuclear reactors, right in the heart of the desert during a global pandemic and ahead of schedule. This is Barakah, the Arab world's first nuclear plant and quite possibly the fastest nuclear construction project in modern history. But speed wasn't their only advantage. While Western nations debated policy and red tape, the United Arab Emirates went from approval to full-scale construction in under 3 years. 4 Korean-designed APR 1,400 reactors, each producing 1,400 megawatts, built in the middle of a desert with cooling systems adapted to blistering heat and salty sea air. The design was chosen for reliability, not experimentation. South Korea's proven APR 1400 pressurized water reactor, a model already operating successfully in South Korea. Barakah's site was flattened, reinforced, and prepped in 2011. Just 2 years later, construction was already underway. Building nuclear reactors in 50 degrees Celsius heat required specialized concrete mixes, advanced cooling strategies, and careful coordination with seasonal sandstorms. Engineers had to design intake systems that could handle salt corrosion and thermal expansion in extreme conditions. By 2020, the first unit began delivering power. Today, 3 out of 4 reactors are online, feeding electricity into a national grid once powered almost entirely by fossil fuels. The final unit is approaching completion. This isn't just about keeping the lights on, it's strategy. The UAE wants to diversify from oil, cut carbon emissions, and become a net energy exporter, not just in barrels, but in kilowatts. Barakah supplies up to 25% of the country's electricity, displacing natural gas and setting the stage for hydrogen production and water desalination. Built at a cost of $24.4 billion, the plant required workforce training, regulatory cooperation with the IAEA, and building a nuclear oversight body from scratch. The UAE even sent dozens of engineers abroad for specialized training. Baraka proves nuclear can work, fast. But what if you could make it even safer? What if you could build reactors that literally cannot melt down? China thinks they have the answer, and it involves something the West threw away 50 years ago. Hidden in China's western desert sits a reactor that doesn't look like any other nuclear plant on Earth. No giant cooling towers, no pressurized water. Instead, it runs on molten salt and an element America tried in the 1960s and abandoned. If this tiny prototype works, it could make every other reactor in the world obsolete. But there's a catch, one that killed the technology once before. In the deserts of Gansu province, far from China's megacities and coastal power plants, sits TMSR LF1, a small, unassuming reactor tucked into the highlands of Wuwei. It doesn't look like a revolution, but it might be one. Instead of uranium rods submerged in pressurized water, this prototype uses molten salt as both fuel and coolant. The fuel, thorium mixed with enriched uranium, is dissolved directly into the salt. If it works, it won't need a massive water source. It won't melt down. And it could run on thorium, an element China has in abundance. It's not China's biggest reactor. It's not even connected to the grid. But in terms of long-term strategy, it's one of the country's boldest energy plays. Because if they can make molten salt reactors viable, they could reshape nuclear energy from the ground up. Safer, cleaner, and immune to the water wars that plague conventional plants. But here's the risk. Molten salt designs have been tried before. The US built one back in the 1960s at Oak Ridge. It worked briefly and was shelved. The salt corroded the pipes. The complexity overwhelmed the engineers. The world moved on. Now, China's picking up where others left off, betting that better metallurgy, advanced sensors, and centralized planning can finish what others abandoned. The first version of TMSR LF1 began testing in 2021. It's tiny, just 2 megawatts, but it's a testbed for something much bigger. A 373-megawatt commercial reactor already under development. Success here would give China a foothold in next-gen nuclear, one that doesn't rely on uranium imports, sprawling cooling systems, or Western technology, one that fits neatly into their broader energy roadmap, secure, scalable, and exportable. But if molten salt reactors seem impossible, what we're about to see next is trying to bottle the power of stars themselves. And the price tag? It'll make China's experiment look like pocket change. What if I told you that right now, in southern France, 35 countries are building a machine to hold plasma 10 times hotter than the sun? Not in space, not in a lab, but in a steel chamber the size of a cathedral. This is ITER, the most ambitious scientific project in human history. It's already cost over 25 billion euros. It's a decade behind schedule, and it might be humanity's best shot at unlimited clean energy. What if you could hold a star in a steel jar? That's the dream. Burning quietly in southern France, where the largest fusion reactor on Earth is coming to life. It's called ITER, Latin for the way, but its path has been anything but smooth. Beneath its 73-meter steel building lies the heart of an idea humanity has chased for over 70 years. Nuclear fusion, the same process that powers the stars. A fire that doesn't burn fossil fuels. That leaves no long-lived radioactive waste. That can't melt down or be weaponized, if it works. ITER isn't just a reactor, it's the largest scientific collaboration in human history. 35 nations, including China, the US, Russia, and the EU. Built with over 23,000 tons of superconducting magnets, cooled to colder than outer space. 1 million components shipped from all corners of the world, assembled like a cosmic jigsaw puzzle with millimeter precision. But here's the tension. ITER doesn't generate electricity. It's an experiment. A 25 billion euro bet that we can confine plasma 150 million degrees Celsius in a magnetic field, long enough to prove fusion is viable at scale. Inside the complex, workers are racing to finish the reactor's core, called a tokamak, a donut-shaped vacuum chamber where hydrogen will be heated to 10 times the temperature of the sun's core. That heat will force atoms to fuse, releasing massive amounts of energy. At least that's the theory. No fusion reactor has ever produced more energy than it consumes. Not once. ITER aims to be the first, producing 500 megawatts of fusion power while consuming only 50 megawatts to sustain the reaction. The engineering challenges are staggering. The tokamak weighs 23,000 tons, as much as 3 Eiffel Towers. The superconducting magnets must be cooled to minus 269 degrees Celsius, while containing plasma at 150 million degrees Celsius just meters away. The margin for error is zero. and the pressure is building, technically, politically, financially. What was supposed to be operational in 2016 is now expected to begin first plasma tests around 2034. Critics call it a monument to delay. Supporters call it the moonshot of energy. But if ITER works, even once, it could mark the beginning of a post-carbon civilization, a world powered by hydrogen, not oil, by physics, not combustion. While ITER chases the impossible, others are making the difficult look easy, including one project that's tunneling under the ocean floor. On England's coast, workers are boring tunnels deep beneath the seabed, not for trains or cars, but to cool the most expensive nuclear project in European history. This is Hinkley Point C, a £46 billion gamble on nuclear power's future in Britain. And if the price tag doesn't get your attention, the engineering will. On the coast of southwest England, two massive reactor buildings are taking shape. What started as a £16 billion build has ballooned to nearly £50 billion. The deadline? Now pushed to 2031, more than a decade later than first promised. Hinkley is being built with the European Pressurized Reactor (EPR) design, the same technology used in China's Taishan plant. Each unit is rated at 1,630 megawatts. Together, they'll produce enough electricity for 6 million homes. But the real engineering marvel is hidden underwater. To keep the reactors cool, engineers are tunneling 5.5 kilometers beneath the Bristol Channel seabed, the largest excavation project in UK history. Seawater will flow through these massive underwater pipes, creating one of the most complex cooling systems ever attempted. Construction has faced challenge after challenge: COVID shutdowns, skilled labor shortages, Brexit-related delays, and rising materials costs. But the biggest challenge has been the EPR design itself, powerful but notoriously difficult to build. Similar projects in Finland and France have faced similar delays and cost overruns. Still, the strategic case is clear. The UK is shutting down its coal plants. North Sea gas is drying up, and wind and solar can't always fill the gap. Hinkley's 3.2 gigawatts of steady nuclear power could become the backbone of Britain's energy future. More than 10,000 workers are now on site. Huge prefabricated pieces are being lowered into place by some of the largest cranes in Europe. And even as critics raise alarms over the cost, the UK is already planning a sister project, Sizewell C, based on the same blueprint. Hinkley is a gamble on scale, complexity, and persistence. But if it succeeds, it could prove that nuclear power still has a future in post-carbon Europe. But what if you didn't need to build on land at all? What if your nuclear plant could float anywhere in the world? Russia has an answer, and it's already switched on. Floating in the Arctic Ocean, powering a Russian town that's literally at the end of the world, sits something that sounds like science fiction: a nuclear reactor on a barge. It's called the Akademik Lomonosov, and it's the world's first operational floating nuclear power plant. Why? Because this part of Russia is vast, remote, and nearly impossible to power through traditional means. Lomonosov was Russia's answer: a mobile reactor that could be built in a factory, floated to a site, and plugged into the grid. No roads, pipelines, or fuel trucks required. The plant holds two KLT-40S pressurized water reactors, similar to those used in Russian nuclear icebreakers. Together, they produce 70 megawatts of electricity and 50 megawatts of heat, enough to power a town of 100,000 people while providing heating during brutal Arctic winters. Building it wasn't easy. The idea was first approved in 2006, but construction delays, rising costs, and global criticism slowed progress. The Lomonosov wasn't fully deployed until 2020, after being towed more than 4,000 kilometers from St. Petersburg to the Arctic Ocean port of Pevek. The engineering challenges were unique. The reactor had to operate in temperatures reaching minus 50 degrees Celsius, withstand Arctic storms, and provide power to a grid at the edge of civilization. The barge-based cooling system designed for marine conditions represents a completely different approach to nuclear engineering. Construction cost came in at around $232 million, and Russia is already planning more floating plants to replace aging diesel generators across the far north. The design has sparked international debate. Supporters call it a model for delivering clean energy to remote or disaster-hit areas. Critics worry about nuclear accidents at sea, but Russia isn't waiting for consensus. Lomonosov has been operational for over 4 years, proving the concept works. This floating reactor may preview what's coming, especially as countries look to power remote outposts, offshore facilities, or even space missions. In the Arctic, Lomonosov isn't just an experiment. It's already keeping the lights on. Floating reactors might seem extreme, but they're nothing compared to what happens when you turn an entire mountain into a battery. North of Beijing stands the world's largest battery. It doesn't use lithium, it doesn't use chemicals. It uses something humans have known about for centuries, but never at this scale. This is Fengning, and it's rewriting the rules of energy storage using nothing more than water and gravity. The concept is elegantly simple. When China's solar panels and wind farms produce more power than the grid can handle, Fengning stores it. Water is pumped uphill to a man-made reservoir carved into the mountainside. When demand rises, that water is released downhill, spinning 12 massive reversible turbines and sending power back into the grid. Construction began in 2013 and took nearly a decade to complete. Engineers blasted tunnels through solid rock, built 2 massive reservoirs at different elevations, and placed most of the machinery deep underground. The site was chosen for its height difference, stable geology, and direct access to Beijing's high-voltage transmission lines. Fengning can generate 3,600 megawatts, enough to power a small country. But more importantly, it helps China's energy grid stay stable. It smooths out the dips when solar production drops. It fills in the gaps when wind dies down. It acts as a shock absorber for a grid increasingly dominated by variable renewable energy. The cost? Just under $2 billion. But for China, this isn't a one-off project. It's a blueprint. Dozens more pumped hydro facilities are being planned as part of their renewable energy strategy. The scale is staggering. The upper reservoir holds 67 million cubic meters of water, enough to supply Beijing for months. The underground powerhouse, carved from solid rock, houses turbines the size of buildings. Fengning doesn't look like a battery. No sleek panels or gleaming towers. Just 2 lakes connected by underground channels with water moving up and down like the tide. No fuel, no emissions, no rare earth minerals. Just gravity, engineering, and scale. While China moves mountains to store energy, our final project proves that sometimes the most powerful forces are the ones we barely notice. In New Zealand, they're tapping into something that's been burning for millions of years. Not coal, not gas, but the Earth's own fire, rising silently from volcanic heat deep underground. Outside Taupo, on New Zealand's North Island, steam rises naturally from the ground, not from industry, but from the planet itself. Here, the Tauhara geothermal plant taps into a vast underground steam field fed by volcanic activity. Geothermal energy isn't new, but what's happening in New Zealand is different. The Tauhara project, completed in 2024, represents precision engineering applied to one of Earth's oldest energy sources. At its heart is a 152-megawatt facility that uses controlled drilling, closed-loop steam systems, and reinjection wells to ensure the heat source never runs dry. Engineers had to carefully map underground reservoirs thousands of meters below the surface, balancing steam withdrawal with long-term sustainability. The entire system is designed to return used water back underground, where it's naturally reheated for continuous use, like a rechargeable battery beneath your feet. But this isn't just about engineering. It's also a cultural effort. The project works closely with local Maori iwi groups, ensuring traditional land rights are respected while sharing the energy benefits with local communities. The Tauhara plant now supplies clean baseload power to hundreds of thousands of homes, with 0 emissions and no fuel supply chain. Unlike wind or solar, geothermal runs 24/7, regardless of weather. It's renewable energy that never stops. New Zealand already generates more than 17% of its electricity from geothermal, one of the highest shares in the world. And with more volcanic zones mapped and ready for development, it's quickly becoming a global model for clean, reliable baseload power. No steel domes, no reactor cores, no floating barges, just pressure, steam, and one of Earth's oldest forces, rising quietly from within, powering the future with fire that never burns out. They tunnel through mountains, float through ice, and draw power from molten rock, splitting atoms and spinning gravity into electricity. Some are live, some are stalled, a few may never work. But together, these megaprojects aren't just chasing energy, they're chasing the future itself. A world where power doesn't come from what we dig up, but from what we engineer. From fusion's impossible fire to gravity's reliable pull, from thorium's quiet promise to geothermal's ancient heat, the race to power tomorrow is already underway. And the winners won't just light up cities, they'll light up centuries. So which project left you stunned? The floating reactor powering the Arctic? The mountain battery storing gravity? The fusion reactor trying to bottle a star? Let us know in the comments. And if this journey through the world's most daring energy experiments sparked your curiosity, hit like, subscribe, and ring the bell for more mega build stories.